Okay, hello class. So in this video, we'll continue on example 8, right, where we had this problem where we had this model that we came up with in example 7, where we could model the velocity of an object at a given time t, where the object is being dropped, vertically. So it's just moving in one-dimensional motion vertically straight down. And we saw we can model this by this differential equation. And we got this by just doing some simple physics and some simple calculus. Now, in this particular example, we said that we wanted to look specifically at the case when there's no air resistance. If you remember, this is the force that came from air resistance. So if there's no air resistance, we basically set that equal to 0. So that simplified our model a little bit. Right? Got rid of that extra coefficient or that extra term. Now from this, we saw we can find solutions to this differential equation. Right? We first divided both sides by m. Then we just integrated both sides, and we got a general solution. Right? And I'll explain what general means, so actually let me not use that notation for now. We got all possible solutions. All possible velocity functions that satisfy this differential equation had this particular form: negative g times t plus an arbitrary constant c. Now, we also saw that we were given an initial condition, right? Specifically, that the initial velocity was 5. We translated that to a mathematical equation. If velocity is v, since t equals 0 determines right when we let go of the object, that's the initial velocity, right? The velocity when we plug in t equals 0, that should be the initial velocity, and that's going to be equal to 5 just by the given information that the initial velocity is 5. So we translated that initial condition to v of 0 equals 5. Then what did we do? We plugged that into this general, again, I'm saying general, into this form of solution, right? We have v of t has this form, negative g of t, negative g times t plus c. But again, this was called an initial condition because it conditions the possible solutions that we can have. Not all of these functions that look like negative g times t plus c are solutions. In fact, if we plug in v of 0, right, just replace t with 0, and then set that equal to 5, we see that we can actually solve for a specific constant. And that constant was 5, which means that the specific velocity function that satisfies this differential equation with this initial condition is negative g times t plus 5. Now, as I mentioned, what we still need to do is that the problem was asking for position. So right now we have the velocity of the object at a given time t. We're looking for position. But as I said before, we have this relationship between velocity, basically position, velocity, and acceleration. If s of t is position, then velocity is its derivative. So I know I'm repeating this, just so it's clear. And acceleration is a derivative of velocity, which is the second derivative with respect to time of position. So just as before, you can see this as either one of two ways. Either you can rewrite v of t as s prime of t, or you can do this sort of model that I drew before where we have s of t and v of t, and then we want to go upwards, and then how do we do that? We do that by integrating with respect to time, because we're taking the derivative with respect to time. And again, here, even though I just wrote s prime of t, it should be clear that this is the derivative of s with respect to t, right? Why? Because t is our only independent variable. So again, I'll make shortcuts like this. If it's clear what variable we're taking the derivative with respect with, I'll just write s prime instead of s ds dt, for example. But if you're comfortable, you can certainly write this as ds dt if this is better for you. Negative g times t plus 5. Either way you want to write it is fine. What matters is that if we want to get to position, we want to solve this new differential equation. Again, notice this is a differential equation, so we have a derivative, and it's ordinary because we have derivatives only with respect to one variable. So solutions to this function are going to be position functions s that we can plug in and satisfy this equation. And as we saw before, how do we solve, or what's the general method? You integrate both sides. So let's go ahead and do that. Then again, we're integrating with respect to t. Simplify both sides. An antiderivative for ds dt is, of course, s by definition. Because what's an antiderivative? A function whose derivative equals ds dt in this case. Well, derivative of s equals ds dt. So s is an antiderivative. We have the constant because it's an indefinite integral. And here we just integrate both terms separately. And of course, plus a constant. Then again, I'm going to combine the constant c and d. They're arbitrary, so I can combine them, and I still get an arbitrary constant, which, like I said, I'm usually going to call c. So instead of d minus c, I'm just going to write c. And this is our function s. So what is this? This is all possible functions, infinitely many of them, that satisfy this differential equation. So I have infinitely many position functions that satisfy this particular differential equation. Now, we're given more information though. We're given that the initial position is 100 meters, which I drew in my diagram here, but we actually haven't used in anything here. Right? We haven't used that initial condition. We used the initial condition that the initial velocity is 5. We haven't used the initial condition that the initial position is 100. Okay. And then just as before, how can we write that initial condition mathematically? Well, again, t equals 0 corresponds to the time where we not let go, but since the initial velocity is greater than 0, we push the rock downward. But t equals 0 corresponds, for all purposes, to the beginning of our system, when the rock starts to fall. So if we're given that the initial position initial position is 100, well, how can we write that mathematically? Well, that's the position when t equals 0. Right? So s plugging 0 for t, and that should be equal to 100. And again, this is called an initial condition just as well. So this is also an initial condition. Why? Because it happens at the beginning of our system at time equals 0, and because it's going to condition the possible solutions that we have for this differential equation. In particular, not every function of this form is going to satisfy this condition. So how do we find the ones that actually do? Well, we again have to just basically plug in 0 for t into our general, again, not general, into our possible forms of solutions. And we know that that should be equal to 100. And basically with this, we can solve for c to get the specific position function that satisfies this model, this differential equation, and this initial condition. Let's go ahead and do that. So what is this equal to? 0 squared is 0. 0 times anything is 0. So we get 0 for this. 5 times 0 is 0. Here we get, so all we're left with is c equals 100. So what is the position of this object that we're letting go of at a given time t greater than 0? Well, as we found, this is precisely negative g. And then remember, g is the acceleration due to gravity, plus 5t plus 100. So again, we started with infinitely many position functions that satisfied this differential equation, but with the initial condition, we went down to precisely one position function. And this is the function that exactly models our particular system that we have. Now, if you look at this, this probably looks familiar because if you've taken Calculus 1 or physics, you should see that this is precisely the function you see for modeling one-dimensional falling where there's no air resistance. And you usually see it written as V naught T plus S naught, where V naught is initial velocity, like we saw in this model. And then S naught is initial position. So in physics and in Calc 1, you're usually just given this model, immediately, and you're not told where it comes from. Here we saw precisely how to come up with this position function that models that motion of that object as it's falling. So now you can see the power of differential equations. The model for this system ended up being a differential equation. In order for us to find solutions for it, well, we had to know how to find solutions of differential equations. And this is very common. Again, in a lot of models, you're going to have changes of things or things that change with respect to time, things that change with respect to position, etc. All those things are usually going to be ended up being written mathematically as derivatives. So when you put them in equations, they're going to be equations that have derivatives, aka differential equations. So hopefully here with this example and the previous example where we actually came up with this model, my goal is to show you that now you have the tools to start coming up with some of these things by yourself. You don't have to be given the model to begin with. You can start with information that you have, write that information mathematically, and come up with a model that actually gives you what you want. So very powerful stuff. Now, I'm going to show you more models that we can come up with, again, just using our knowledge of calculus, differential equations, and potentially physics in the next video. But for now, this is your first introduction to modeling with differential equations. This is what it looks like.